Welcome to Quadratic Functions, Lesson 60. Here's my working definition of a quadratic function. What is it? It's basically a square function, which means x squared. And you could have transformations applied to it. So, hence the previous lesson on transformations. It might get shifted up, down. It might get reflected. It might get moved, whatever. It might get stretched is another good one. Anyway, so we're going to play with quadratic functions. And to get started, we should take a really good close look at the standard untransformed, if you will, the pure square function, f of x equals x squared. It's going to be the parent function all the time, so it will be worth it to get a really close look at this thing. So I'm going to plug in more points than usual. Usually I just do the shotgun, -2, -1, and so I'm going to start at -3. Whoa. And I'm going to plug in -12. Whoa. As well as on the positive side over here. Let's get a really good look at this function. So, all you got to do is square it, right? Look at me with the y. Aren't I silly? That's better. Okay, so what we're going to do is we're going to take the x and square it. That's all you got to do. -3 squared, 9. -2 squared, 4. 1. Half, that's a fourth. 0. Fourth. 1, 4, 9. Cool. So we graph this thing real quick. So at -3, we're off the chart. At -2, I'm at y equals 4 right here. At -1, I'm at 1. At -12, I'm at a fourth. That's something like that. Nah, I don't like that. Something like that. Okay. Then we're at the origin, 0, 0. 1/2, 1/4, 1, 1, 2, 4, and then 3, 9, which we don't reach today. And then if you try to join these nice and smoothly, try not to just use straight line segments. That's a little on the gross side. Trying to sort of, be true to the curvature of this thing. This thing has some curvature, right? So you just try to do it the best you can, and you say, there, I got it. Now, 4 key features I would like us all to be aware of here. 4 key features of this graph. Key feature number 1. This one's obvious. It opens up. Right? If you think of this as the mouth or whatever, the thing is opening up. Okay, we know that. What else is a key feature? Well, this part down here is called the vertex. So the vertex is at the origin. For the basic square function, the vertex is at the origin. We'll be moving it around later. But for now, for the basic square function, the vertex is at the origin. What's another key feature? Please notice it's nice and rounded. Don't make pointy parabolas. They kind of, I see people draw parabolas like this, and I'm like, no, that's not a parabola. It looks like an absolute value function. Make your function look true to its... Come on, eraser. Make your function look true to what it really is or whatever. Okay, now for the big one. This is the really cool one. You ready? You ready? I'm going to put this in red because it's actually kind of important. In fact, this is the whole reason I'm doing this. This is really cool feature, and you may have seen this somewhere before, but I'm going to use it a lot. How should I say this? From the vertex. Once you know where the vertex is, you can draw this. You can draw let me call it a standard parabola. It's just x squared, the standard parabola. Parabola. I ran out of space. There it is. You can draw it by doing this. From here, go over 1, up 1 to get to your next point. Over 1, up 1. From there, over 1, up 3. Ooh. Over 1, up 3. From there, you would go over 1, up, well, let's see, we got to get from a 4 to a 9, right? Up 5. Do you see the pattern here? Over 1, up 1. Over 1, up 3. Over 1, up 5. Next would be over 1, up 7. And so what's so nice about this is you'll see me oftentimes, and maybe I'll label this up 1, up 3, up 5, and so on. Um, I can like skip over making an XY table. That's how you know you're getting happy, is when you don't have to keep making XY tables all the time. Ooh, nice siren out there. Must be Wednesday at 1 o'clock, huh? Anywho. So anyway, I'm going to use this a lot, like a lot. If it's just an x squared, and I don't care if it got shifted or whatever, because when you start at the vertex, is the point, you can just go over 1 up 1, over 1 up 3, over 1 up 5, over 1 up 7 to get all the rest of your points. It works nice. Just try to be nice and rounded down there. So, okay, so let's see. We're going to make a graph of negative 2x squared real quick like. I'm not even going to need an xy table. Not going to need it. Okay, so I notice that it is an x squared function, but somebody went and changed it, right? Now, from the previous lesson on transformations, we see here that, how should I say it here? It's been, well, what's the negative do? It's been reflected over the x-axis, which means it's going to be upside down. It's going to open down, not up. Well, that's not too tough, because instead of going over 1 up, I'll go over 1 down, over 1 down. Okay, so it'll still be kind of the same. So it's negative, so it's reflected. And what else? The 2. The 2 means that it's been vertically stretched by a factor of 2, i.e., it goes up twice as fast. And so what does that mean? Maybe I'll use a different color for this. What that means is we're not going to go over 1 up 1 and then over 1 up 3 and then over 1 up 5. We're not going to do that. We're going to go over 1. I don't have to keep writing over 1. We're going to go over 1. We're going to go, well, let's take into account both things. We're going to flip, which means down twice as far. So it's going to be a down 2, down 6, down 10. And by down 6, we mean down 6 more, right? Remember what we were doing up here. I went over 1 up 1, over 1 up 3 more, over 1 up 5 more. Make sure you keep that clear. Anyway, that's really all I got to do here. So I'm going to do it. I'm going to do it right now. So let's see. Well, there's no shifting, right? We didn't translate left, right, up, down, or anything. So we know the vertex is still at the origin. So I'm going to just kind of go like this. There's where the vertex is. And now from there, I'm going to do this. Over 1, down 2. Over 1, down 2 puts me here. And of course, it's going to be symmetrical on the other side. Might as well do it on both sides. Then I go over 1, down 6 more. 1, 2, 3, 4. Oh boy. 5, 6. All the way down to here. Look at that. Same thing on the other side, right? And that's enough points. You get the idea. I drew that parabola real quick like. I didn't even need an XY table. Didn't even need it. I hope you thought that was cool. Now, continuing with this theme, what's the theme? The theme is that you have a basic square function. This one is always in the back of your mind, and then you look at a big fancy equation somebody gives you. You say, well, wait a minute, it's still x squared. It's still a quadratic. It's just that it's been moved. We have lots of transformations this time. So let's see. Let's pick apart our transformations. Well, it's not negative. There's not a negative, so it opens up. That part's the same as usual. That's cool. That's supposed to be an arrow. Now the 1/2 here tells me not a vertical stretch, but a vertical compression by a factor of 1/2. So in other words, it's going to climb half as fast. So not over 1 up 1, over 1 up 3. No, it's going to be over 1 up 1/2, over 1 up 3/2, which is 1 1/2. Over 1 up 5 is going to become up 5/2, which is 2 1/2, and so on. So we're going to go over 1 up 1/2, over 1 up 1 1/2, over 1 up 2 1/2 more, and so on. So that's what the half is telling me. Now this is cool. Remember what happens when you take a function and you plug in an x plus 3 instead of just an x. In other words, you replace the x itself with an x plus 3. Do you remember what that does? From the last homework. That's going to go left 3. And this minus 4 at the end, that's kind of like taking a function and just subtracting 4. And you remember what that does? That goes down 4. So the vertex, maybe I'll continue this thought over here. Vertex has been moved. It's not at 0, 0. Well, if you move it left, usually it's going to be here, right? It's not there. We moved it to the left 3. We moved it down 4. Guess where we are? We're at -3, -4. Smiley face. So notice that you can read the coordinates of the vertex right there, basically. It's kind of cool. But anyway, we figured it out just from using our knowledge of transformations. So anyway, that's the vertex. Now I was expecting it to open up. So that's good. So I'll label the vertex right underneath it. It's at -3, -4. That's a nice, when it says show all key features, well, that's got to be one of the most keyest of all parabola features is where the heck's the vertex, right? Isn't that always what you want to know? Where the heck's the vertex? Okay, now I can draw the parabola right now. I don't need an XY table because I know the pattern. Usually you go over 1 up 1, but because of this factor of a half in front, I go over 1 up a half on both sides. Usually from there I go over 1 up 3, but now I'm going to go over 1 up 3 halves, or in other words, over 1 up 1 1/2 on both sides. Over 1 up 2 1/2. That'd be just about here. Oh, that's lucky. We just nailed the y-intercept. That's one of the key features, by the way, is where the intercepts. We got the y-intercept cheap. So what did I just do? I did the up a half, up 1 1/2, up 2 1/2, up 3 1/2, up 5 1/2, and so on. By the way, on both sides. Pardon me. Okay, we got enough to draw this, right? It's doing that. Don't forget your arrow points, by the way, to show the continuation. Remember, a graph is a piece of communication. Think of this as almost like an English class, or what do they call it? Composition class, right? Okay, one more thing, though. We haven't really shown all the key features, have we? No, it says show all the key features. The key features, for sure, include the vertex. We got that. Includes the y-intercept. We got that. But, and you know, we've got a really good idea, approximately where the x-intercepts are. But where are they exactly? Where exactly are the x and y-intercepts? Well, we already got the y-intercept, but let's just be official about this so we always remember. You get the y-intercept by evaluating f of 0. And what's our function again? There it is. So it's a 1/2, put the 0 in there, plus 3 squared minus 4. Okay. So the 0 plus 3 makes a 9. Or the 0 plus 3 makes a 3, and then you square it and you get a 9. Notice a half of 9 is 4 1/2. 4 1/2 take away 4 is a half, just like we got before. Good. But just a reminder, that's the standard way to get the y-intercept. And what's the standard way to get the x-intercept? Do you remember? You have to take the whole function, set it to 0. It's usually more of a process. So I'm going to take that function, half x plus 3 squared minus 4. And I'm going to set that to 0, and solving it will tell me at what value of x do you get y equals 0. In other words, where are the x-intercepts? So you might be tempted to start foiling this out or something, but hopefully you might remember back a few lectures anyway. I talked about something called the square root method. X is only here. That's the only place x shows up. It shows up in a square bubble type thing, whatever you want to call it. So what's nice is that you can isolate the square part, add 4 to both sides, multiply both sides by 2, you get an 8. And then, because that's the only place x is, it works really well now to take the square root of both sides. So on the left side, you get x plus 3, and that's it, actually. I don't even need the parentheses. Get that out of there. It just pops out, you know, the square root takes off the square. That's all it does. And then over here, you get the square root of 8. Plus or minus. When does plus or minus show up? If I write radical 8, you do not say plus or minus radical 8 just because. This symbol by itself just means principal root. And the principal root, guess what, is the positive one. Okay? So if this is what you're starting with, no, don't add that in. Okay? But, here, that's not what I was starting with. I was doing an operation. I was performing an operation here. I wanted to take square root of 8. And in that case, the square root, there are 2 square roots. And because there are 2 square roots, and because this symbol only indicates the positive one, you have to put the plus or minus in front to say that you mean both roots. Hope that makes sense. A little piece of math trivia for you, except it's not that trivial. Okay, so we should simplify this. X plus 3 equals plus or minus. Now the key to simplifying a radical is you ask yourself, look, there are certain numbers you can take square roots of, right? These are some square rootable numbers right here. Does the 8 contain a factor of any of these? Yes, it contains a factor of 4, which is square rootable. So you take square root of 8 and you split it up this way. And by the way, yes, if you multiply those two things, you get the square root of 8. So you're just kind of factoring it apart like that, because then you can do this. X plus 3 really is plus or minus. Radical 4 really is a 2. And then you get this square root of 2. Okay. Okay, now, almost there. Remember, we're trying to get x by itself, right? So all we really got to do is subtract 3 on both sides. So subtracting 3, I suppose you could write it out there, but that's not what you just do. Come back out. Come back out. Okay. I suppose you could write it out there, but that's not really the convention. The convention is to tuck the negative 3 in front, like this. Okay, just tuck. You can add and subtract things in any order, right? So the basic idea is to subtract 3 somewhere on the right side. Okay, I subtracted 3 there in front. Fine. So there's your exact forms. Now you got to get out your calculator, because I want to look up at this graph and say, hey, does that look like negative 3 minus 2 square roots of 2 to you? Kind of hard to tell, ain't it? So you get out your calculator, you get the decimal approximations. That's what they're for. Decimal approximations are so you can actually, think in terms of how big is it really. The exact form is the gold standard. You want the exact form because it keeps your full precision. So anyway, negative 3, let's see, I'm going to go minus first. Minus 2 square roots of 2. Boom. I got a negative 5.83 roughly. 2 decimal places is plenty for a graph, right? And then I got the negative 3 plus 2 square roots of 2. And that's about it. Well, it's still negative. It's about a negative 0.17. These are our x-intercepts. X-intercepts. And by the way, on the homework, when it says in both exact forms and as decimal approximations, it means write your answer just the way I've written it right here. Do that. Do that. Get the exact form. The exact form is valuable. It's a piece of precision. It's wonderful. You want it. And of course, you're going to kind of need the decimals in order to look at your graph and say, does that look like negative 5.83? It sure does. Doesn't it? Sure, because I missed. It should have gone over, my curve's a little off. But yeah, that looks good. And that certainly looks like about negative 0.17. Sure. Looks good. Looks good. Okay, so we're grooving now, huh? So I think you're ready. You're primed and ready to see this now. So what we've been working with has a name, actually. It's called the standard form of a quadratic function or a parabola. It's a standard form. It's kind of like, with straight lines, you have this nice, we don't call it standard form. We call that slope-intercept form, but it's the good one. It's the one we like to work with, right? You can write lines in other ways, but that's the one we like. This is called the standard form of a parabola or of a quadratic function. So notice, looking at the form, you can get the vertex right away because we're shifting. Now wait a minute, with the minus it means you shift it to the right. Remember, it's kind of backwards. So the vertex, you would shift to the right by h, and then you would shift up by k. Okay, so just looking at the formula, this is completely analogous to when we had y equals mx plus b, and we just looked at the formula and said, hey, that's the y-intercept, hey, that's the slope. It's the same kind of deal here. You can look at the formula and you can say, hey, h and k, that's my vertex. Cool beans. Then you consider the a after that. Look at the a, and there's a couple things you can do here. If a is positive, you know that it opens up, and if a is negative, remember it got reflected, so it opens down. So just looking here to say, hey, am I starting off with the big old plus or a big old minus? Because that makes the biggest difference in the world. Does it open up or does it open down? So you can just look at the formula again and know which one it's doing. And then another thing you can look at is, and I'm going to put this in absolute value here, but if a is like a big number like 3, 4, 5, 6, then you know that you've had a vertical stretch by that factor, I guess. I'll say factor of a. And if it's less than 1, in other words, it's like a fraction, like a half, a third, or whatever, it's a vertical compression by a factor of the same thing. So if that's a 1/3, it's vertical compressed by 1/3, and so on. The only reason I'm using absolute value signs here is because I'm trying to say, look, I'm not thinking about the sign, I'm just thinking about the number itself, not the sign. So if it's negative 1/2, you would still say, well, the 1/2 is less than 1, so it's vertically compressed, and so on. The negative, of course, does something completely different. It's got nothing to do with the stretch or compress. It's got to do with the reflecting it upside down. So there, this is great wisdom right here. This is great stuff. So now I'm going to start using that. Let's start working with this form right now. Here's a nice thing we can do. We can figure out the function. It has a vertex at negative 2, 4. And a y-intercept at negative 4. Well, if you know where the vertex is, we got basically 2/3 of our formula figured out because I know that's the h and I know that's the k. So I can start writing the function. I don't know what a is yet. I have to write that there as an a. Okay. But x, now it says minus h, but h is negative. So that becomes a plus 2 squared, and then the k is positive, so plus 4. So far, so good. Of course, we've got to get that a. Now think back to our piecewise linear functions, or even just our linear functions. Remember when we had straight line functions and like we knew the slope or something, but we didn't know what the b was? Do you remember how we got the b? We said, well, this equation works for every point on the line, so you find a point on the line, plug in the xy coordinates, and get it. Same exact idea here. This is supposed to be the formula that applies to all points on the parabola. Do we know any? Well, we already used the vertex. You can't use that again. But do we know any other point? Yes, we do. They told us that there's a y-intercept. That would be the point, let's see, when you plug in x equals 0, you get y equals negative 4. So we use this point and say, okay, when I plug in x equals 0, I'm supposed to get y equals negative 4. And so I can solve. Boy, that looks terrible, doesn't it? Let's fix that. That's a 2. Okay, so now we can solve for the a, because I got an a. This is a 2 squared is 4. So I've got a 4a plus 4 equals negative 4. Cool. Subtracting 4 on both sides, 4a is negative 8. Cool. Dividing both sides by 4, a is negative 2. Cool, 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 cool. Because now I can finish my function. That a there, yeah, it's a negative 2. And then we've got the rest is the same. So that's pretty cool. You knew where the vertex was. You knew where the y-intercept was. It doesn't take long to say, I know the whole darn formula. I know the whole darn function. Cool. Cool beans. Now, here's the thing. I like this form the best. That is definitely my favorite form because it is so nice. Hey, there's the vertex. Hey, the A. Hey, the A. But, of course, you know, this being math, there's going to be more than one way to do it, right? So there's always more than one way to do it. So look what happens here. This is a parabola also. I know it because it says x is squared. I mean, another way to define a quadratic function, I suppose, is to say it's a polynomial function of degree 2. That's what this is, a polynomial function of degree 2. That's a parabola. Though I do like saying square function that's been transformed. Anywho, let's do this. Let's maybe in a different color because this is sort of a minorish, pointish, minorish. I'm going to take that function up there that we just played with, this one, the negative 2 dx plus 2 squared plus the 4, and say, okay, let's write that out as a polynomial, which basically means we're going to have to FOIL this all out. So that's negative 2. Now remember, x plus 2 squared means this. Make 2 copies of x plus 2. That's what it means. And when you make the 2 copies, you have to basically FOIL them. X times x is x squared. You've got a plus 2x and a plus 2x again. So that's a plus 4x. And then you have the 2 times 2 is a 4, and then plus 4. So this is a negative 2x squared minus an 8x minus an 8 plus a 4. And so here's our new version of the function. Negative 2x squared minus 8x minus 4. I don't have to circle that. That is funny. You see the joke here? This is a joke. We took the standard form of a parabola. That's what this is, the standard form of a parabola. Converted it to a polynomial in standard form. Right? That's what this is. Ax squared plus bx plus c. And now we call it general form. What the heck happened there? I don't know. I don't know. I don't get to make up the names of these things. But I just think that's the weirdest thing in the world. So if you get a little mixed up remembering which is standard, which is quadratic, I kind of don't blame you. But you can always refer to your notes, right? So anyway, when you take your standard form, when you take your standard form and turn it into a polynomial in standard form, it's no longer a standard form or anything. It's a general, well, it is a standard. It is a polynomial in standard form, but it's called the general form of the parabola. Ain't that something? Now, a couple of notes to make here. I'm going to erase this because that's not really all that important. It was a joke. Remember, it was just a funny joke of the universe. Okay. But there are 3 things to note. The first thing is, notice that negative 2 just kind of schlepped along the whole way. That's nice. Note number 1. It's all the same A. Yeah, I guess I don't like the star. Meaning that, remember, here was our standard form. And when we turned it into this general form, this was still a negative 2. This A here is exactly the same as this A here, which means when you're in your general form here, you can look at that A and decide all the same things. Positive, it'll open up. Negative, it'll open down. Is it bigger than 1? It'll be a vertical stretch. Is it less than 1? It'll be a vertical compression. That part's all exactly the same. I love that. It's the very same A. So that's a big note number 1. Okay, big note number 2 right here. It's not that big, but this one's big. It's kind of big. Note number 2, it's not big, but it's big. Kind of. Okay, so anyway, note number 2. What's that? That is the y-intercept. Prove it to you 2 ways. When we solved it, we got negative 4, right? Did we graph that? Oh, we never graphed it. Never mind. I can only prove it to you 1 way. Where am I? Here I am. When you plug in 0 for x, that goes away, that goes away. You really do get c. Okay, so that's the y-intercept. So that's kind of like a free piece of information at least. So the A has a real meaning. It's the same A. The C has a real meaning. It's the y-intercept. And now for the big note. Number 3. See this B here? By itself, it's not particularly useful, unfortunately. But it's related to the vertex in this way. You can find the h part of the vertex anyway. That would be the x-coordinate of the vertex. Using this formula. Negative, take the b, divide it by a 2a. And I could show you where that comes from. It comes from a process called completing the square. It's in the book. So if you're interested, you can look in the book. But I'd rather just work with it for now. So just take this as received wisdom, I guess. So that's where the h is, and then where's the k? Well, you know, if you know the x-coordinate, you can always just plug it into the function to get the y-coordinate. So this is the vertex. So actually, it's a little more involved, but not that much. It's just a little formula here. So you can still kind of get the vertex out of this formula by using this other formula. Okay, so you take the b, the a, you plug them into that formula, you can get the h, plug the h in, you can get the k. So that's all the things we need to be playing with parabolas, right? So let's see now here. Is this going to be the last example? This is going to be the last example. Cool. So as our final example, we will just, let's play with this general form once, so we can get used to it a little bit. Now, first question. Wouldn't you love to know where the vertex is? I know I would. So that's, I mean, you want a graph of parabola, you want to know where the vertex is, right? So I'm going to use that formula, h equals negative b over 2a. So negative. The b is the coefficient of x, which is 1. And then, of course, there's the a, so it's 2 times the a, which is negative 1/3. Okay. What I like to do right now is I like to say, look, I got a negative times a negative. I know it's positive. Let's just dispense with the signs right now. It's positive. It's positive what? Well, I got a, let's see, I got a 1 over a, and I'm ignoring the sign now because I know it's positive. This is a 2/3. 1 over 2/3, which is a division. How many times does 2/3 go into a 1? Not a lot. The way you do this is you do the division out. 1 divided by the 2/3, and just with fractions, what you're doing is you're multiplying by reciprocal. You can make the 1 look like a fraction by putting a 1 underneath. That's always free. Multiply by the reciprocal, we're getting 3/2. So the vertex is at x equals 3/2, or 1.5. What about the k? Well, you plug this into your function. So I've got a negative 1/3. My x is 3/2 here, squared, plus, plug it in here, 3/2, plus 1/4. So this will give me the y-coordinate. Negative 1/3. Remember, you always do the squaring first, right? As much as I love to cancel 3's, I can't do that because this 3 is busy. It's got this square thing. So square root of 3, I got a 9. Square root of 2, I get a 4. Okay. Plus, well, 3/2 plus 1/4. Okay. Equals what? Okay, now I'm going to cancel. 3 goes into 9 3 times. So I've got a negative 3/4 here. Now this I should write in terms of fourths also, so I'm going to multiply top and bottom by 2 to make that into a 6/4. And then I've got this other 1/4. So this comes out to, negative 3 plus 6 is 3 plus 1. This comes out to 4/4, which by the way is 1. And that's my k. Cool, we just figured out where the vertex is. I'm going to put it over here. H is 3/2, which is 1.5. K is 1. It's right about there. Is this thing opening up or down? It's opening down because of the negative. Why do I care? Because I'm going to label the vertex up here instead of underneath. So it's at 3/2, 1. There's your vertex. That counts as labeling a key feature. By the way, that's the y-intercept, remember? Y-intercept at 1/4, which is right about here. Now, by the way, you know that these parabolas are symmetrical, right? So it's like, if you know that's the vertex, you know it's almost like there's a mirror right down the middle. So if I know this point, I can kind of bounce over to here and say, well, it's going to have a mirror image over there. That's kind of a nice thing about these parabola type stuffs. Now, let's see. How should I do this? You know what would be nice is to get the x-intercepts. I mean, I already kind of see what the parabola is going to look like, don't I? I mean, it's going to have to go something like this, right? Don't even really need any more points. Except, if I want to list all the key features, I should really list what these x-intercepts are. So we already get the y-intercept, right? So the y-intercept is a fourth. Let's solve for the x-intercepts. Then I think we'll pretty much be done. So let's solve for the x-intercepts. Okay. So to find the x-intercepts, you have to solve the function equaling 0. Where does the function equal 0? This is where the function equals 0, right? Along that axis? Well, where along that axis? What values of x? So you take the function in all its glory, the negative 1/3 x squared, and the plus x, and the plus 1/4, you set that equal to 0. I don't think we're going to be factoring that, or at least I'm not in the mood to even try. So you must be thinking quadratic formula, right? But here's a tip. Pre-quadratic formula, or I'm going to call it this way, prep for a quadratic formula. We're going to prep this formula. Before I start plugging in a equals negative 1/3, you really want to plug that into a formula c equals 1/4. I don't want to be doing that. I want to plug in nice numbers. So there's a nice trick called clear the fractions. It only works with equations, but it goes like this. You can't clear, if I didn't have the equal 0, I couldn't clear it, but I do. So I can clear the fractions. How? Multiply through, which means both sides, by, I'm looking at the 3 and I'm looking at the 4 and I'm saying the common denominator is 12. Watch what happens. If I multiply everybody by 12, that means I'm going to, well, I guess I'll write it like this. I'm multiplying everything by 12. This, and the other side of the equation too. So if you have negative 1/3, and then you multiply that by a 12, x squared, and a 12x, and then you take the 1/4, and you multiply it by a 12, and then you take the 0 and multiply it by 12, okay, then all these fractions are cancel. 3 goes into 12 4 times, so I've got basically a negative 4x squared plus 12x plus, and then 4 goes into 12 3 times. Now, isn't that nicer already? That is so nice. I'm going to do one more thing. Now I'll multiply through, which means both sides, by negative 1. And we're going to have to bring this over here. So I multiply by negative 1. That makes that a positive 4x squared. See, that's my point. But then that'll have to be a negative 12x. That'll have to be a negative 3. That'll have to be a negative 0, which, of course, is just 0. Now we're ready for the quadratic formula. We can use nice numbers. A equals 4, B equals negative 12, C equals negative 3. Here we go, folks. Remember the formula? X equals negative B plus or minus the square root, B squared, minus 4 times A times C is negative 3. And then that's all over 2 times the A. Now, a negative 12 is a 12. Plus or minus square root. A 12 squared, whether it's negative or not, it comes out to positive 144. And then this minus times a minus is going to make a plus. And I'm adding what? 4 times 4 is 16, times 3 is 48. And that's all over 8. Okay. 12 plus or minus the square root of, what is that, a 192. Wow. Over 8. Now if you have a calculator, a nice calculator, like I have a Casio FX115ES, or there's others that are good, 300ES is good too. You can actually type in square root of 192 and it'll tell you the answer. The calculator is telling me 8 square roots of 3. So get yourself a nice calculator and then take advantage of utilize technology, man. It's good for you. Even better for you, of course, is if you know how to do this. I'll show you how to do this down here. How do you simplify the root of 192? Well, remember what I was saying before. we have square rootable things. Some square rootable numbers like this, like this, like this, like this, like this. So it's probably easier to think in terms of, does 4 go into 192? And it does. Let's see, 4 and a 19, 4 with 3 left, 4 and a 32, 8. Boom. And then you look at the 48 and you say, oh, that's a 4 times 12. Woo! And then you look at the 12 and you say, oh, that's a 4 times 3. So notice what we got here. We got the square root of, now I'm going to multiply these together. 4 times 4 times 4 is 64. And then, of course, times a 3. So that's the square root of 64 times the square root of 3. And so that's 8 square roots of 3. Same thing as the calculator told us. Okay? So if you're trying to stave off dementia, which you're probably not worried about it if you're only in your 20s or 30s, but sooner or later you're going to want to do this kind of stuff. Use your mind on all kinds of puzzles, right? And this is better than Sudoku. This is cool. Simplify some radicals. They should put that in the newspaper. They really should. So anyway, whether you do it this way, whether you do it this way or you do it by plugging in your calculator, either way, this is going to be 12 plus or minus 8 square roots of 3 all over 8. Now, you can think of this as two fractions. And if you look at it as two fractions, you're going to say, oh, heavens, I should be canceling here. I should be canceling 4s. 4 goes into 8 twice. 4 goes into 12 3 times. Or here I can cancel 8s if I wanted to. So you could say 3 halves plus or minus square root of 3. You could say it that way. Or here's another way to cancel. So let me erase all that again. The main reason I wanted to show you that you think of it as two fractions is so that when you go canceling, you're canceling everywhere. Everywhere. You can't just pick 2 spots. You have to pick all 3 spots. I'm going to cancel 4s. So 4 goes into 8 twice. 4 goes into 12 3. 4 goes into 8 twice. And so here's our really cool form. 3 plus or minus 2 square roots of 3 over 2. Now if you wrote it the other way that I just erased, that's fine. It means the same thing. But this would be the proper way to cancel, just so you're aware. You have to cancel in all 3 locations. I'm canceling 4s because there's 4s in all 3 locations, and when I do, I end up with this nice answer. So that would be the exact form for the x-intercepts. If you want to get the approximate forms, I already punched this on my calculator. I got a negative 0.23 for one of them, and I got a 3.23 for the other one. Now, on this graph, does that look about right? Negative 0.23? Well, yeah, sure. Does it look about right? Positive 3.23. Sure, looks good. Looks good. It's always good to have a reality check. Okay, as a parting shot, so to speak, I want to show you something slick. Now it says rewrite f in standard form. That means the a times the x minus h squared plus the k. Now you might be thinking, oh my gosh, that's going to be a chore. But it's not. It's so simple. For one thing, we already got the h and the k, right? We solved for the vertex. Way up here someplace. Where is it? Didn't we? Oh, there it is. We solved for the vertex. It's 3 halves comma 1. So it's 3 halves goes there, the 1 goes there. And as for the a, remember the point on the previous page, it's all the same a, right? I was saying that over here, it's all the same a. Here's the a for this formula, negative 1/3. It's going to be the same a for this formula, negative 1/3. And so we actually, bada boom, bada bing, negative 1/3 x minus 3 halves squared plus 1. Wasn't that fun? All right, well, that's a nice whirlwind coverage of everything you ever wanted to know about quadratic functions, except that we're going to have lesson 61, which is we're going to apply these things to real life, which will be, in my mind, that's the fun part.